So guys, welcome back. Today we try to finish section 4.3 about the Kronecker product. If you remember last time, we started talking about the Kronecker product, and in fact, we talked about the Kronecker product, its definition, and how to use it to perform a two-dimensional discrete transform. And today, my plan is to talk about the Kronecker sum and how to use it to get the eigenvalues and eigenvectors of the Kronecker product and the Kronecker sum, and how to perform matrix to vector operation. So just a quick review. So last time we said that this Kronecker product is defined as, in fact, how do we define? So K, which is A by B, the right symbol used in LaTeX, if you wish, both times, was to do what? I have an example, I'll skip to it. So for example, A by B is in fact a block matrix where every item of A is multiplied by B n base. Okay? So basically you obtain a n by capital N matrix, if you wish. Okay? And we work in the simpler case, where the simplest case where we had I2 by I3 matrix, and we got an I6 matrix. And there are other cases, but we generally talked about the properties. We said that the Kronecker product of AB dot the Kronecker product CD is AC multiplied by BD times by the Kronecker product. And if you multiply AB using the dot product by N inverse B inverse, you get I by I. Okay? So we worked up a couple of examples. Today I would like to continue and show you the Kronecker sum. Okay, so where it is, I'll talk here about the Kronecker sum. Okay, here, the definition. In fact, a 2D Fourier transform is the product of two steps. First of all, transform by rows, and a transform of the result by columns. Okay, and those steps are the Kronecker product I by omega and omega by I. Here, I'm defining if A is m by n, so it's a square matrix, and B is a n by n, the Kronecker sum is simply obtained using two Kronecker products. So it's the Kronecker product of A by In, which is the identity matrix of size n, plus the Kronecker product of the identity matrix of size n by B. So you get m by n by m by n. So for example, if we have these two matrices, guys, so now listen up. If you have these two matrices, what is A multiplied by In using the Kronecker product? So this is a 3 by 3, okay? And here, what is M and what is N? M here is 3, capital N is 2. So if I multiply by the identity matrix of size 2, what do I have? I will have A here and A here. You got it? Now, if I multiply the identity matrix of size M, which is basically 1, 1, 1 in the diagonal, by B, what do I get? In times E, you get the following. By the Kronecker product, is the following matrix. Basically, you're going to have B, B, B. Okay? Don't forget, every row of B, that B is 2 rows. So you get the 6 by 6, basically. And here you get also a 6 by 6. Which means you can perform the sum. Got it? But Shabab, is that clear? So now you can perform this. And basically this is the Kronecker sum. So there are a couple of identities. First of all, For the eigenvectors, let x be an eigenvector of A. Of course, it means that AX equals lambda x. And Y be an eigenvector of B, which means that by is equal to mu y. So if A is n by n, and B is capital N by capital N, then X is n by 1, and Y is capital N by 1. So because we have two respective eigenvectors. So the Kronecker product has a size n by capital N. And we found out that the Kronecker product of X and Y is an eigenvector of A by Y, or by B. Okay? So in fact, the Kronecker product xy is a vector of length n by n. And the corresponding eigenvalue is lambda u. So basically in mathematics, it means that if you have, if here we are trying to do what? We are trying to solve this eigenvector problem for this matrix A multiplied by B using the Kronecker product. Okay? So if you decompose it using the properties we've seen earlier for the Kronecker product, the Kronecker product AB multiplied by the Kronecker product XY, you can write it as AX Kronecker product by BY. Okay? Since AX itself is lambda x and BY is mu y, and these items are just scalars, you can put them outside. So basically, you have the Kronecker product, the eigenvector of the corresponding eigenvector of A by B is basically just the Kronecker product of X by Y, and the corresponding eigenvalue is lambda. Okay. Now you can also talk about the same thing, same pattern for the Kronecker sum. So what do we have here? If you're trying to find the eigenvector of the Kronecker sum, A plus B, okay? Then you will find out that the corresponding eigenvector is the Kronecker product X by Y. But the corresponding eigenvalue is lambda plus mu. The corresponding eigenvalue is lambda plus mu. Why is that happening? Because Y is an eigenvector of the identity matrix, In. Similarly, X is an eigenvector of the identity matrix of size small n, and that corresponding eigenvalue is 1. And that equation 13 for the Kronecker sum just comes from the two applications of 12, the previous equation, the previous slide, 12 for the Kronecker product. And you add up, you get the lambda plus mu eigenvalue. Okay? So the last thing I would like to show you is how useful it is to use what we call vectorization of a matrix. So in fact, we often want to vectorize a matrix, and you see that this provides a complexity gain to perform large operations. So we often want to vectorize a matrix. So starting by an m by n matrix, okay, we stack its n columns to get one vector. We call it vec of A. And its length is n by n. So this matrix, which was composed, in fact, you put the column one after the other. So the vectorization of A, B, C, D gives you A, B, C. Okay? And we have, let me just check something. Maybe I did a small mistake. ACBD, sorry guys. This should give you, yes, this is what I had. It should give you ACBD, yeah? ACBD. Okay, so you put the columns one after the other. So, in fact, we have this property that the vectorization of A times B times C by the regular dot product, and we are assuming here that the three matrices A, B, and C are n by n. They are square matrices of same size, is equal to the Kronecker product of CT by A times the vectorization of B. And this is very useful. So if the three matrices A, B, C are n by n, then A, B, C is in fact n by n, and the vectorization makes it n squared by 1. Okay, the vectorization is of size n squared by 1. Now, on the other side, the Kronecker product n squared by n squared is n squared by n squared. I'm talking about this, CT by A. Okay? And it multiplies the n squared vector here, vectorization B. Okay? So the right-hand side of 19 has also a length which is n squared. Okay? Why is it useful? It provides a complexity gain. So if A, B, C is m by p, then CT A, Kronecker product, has n rows as it should. And notice a big difference in the operation count. So in the case n by n, the two multiplications ABC need 2 times n cubed separate multiply adds, while the Kronecker product on the right needed n to the power 4 entries. So you see the difference. If n is huge, you have a huge complexity gain. So if you don't notice that it is a Kronecker product, this matrix multiplication needs n to the power 4 multiply adds. So what we call reshaping is the application of the vectorization to take advantage of the Kronecker structure. So, for example, for the linear system, if you assume that B is x1, x2, and C is a 2 by 2 matrix, the right side of 19, in fact, is simply a matrix vector multiplication. So we assume here that kx. So if you assume that x is the vectorization of B, then k is the Kronecker product CTA. So we can write down that y equals to kx. Here I just substitute k by CTA, CT Kronecker product CTA by x. This is okay. So this derives you, in fact, the vectorization ABC. And at the end of the day, you see that the pixel values in 2D, this is used in images to reduce the size of operations that are needed, and use it also in the framing of videos. Okay, so this is all what we needed for 4.3. Inshallah, we'll get back to it to do a small polishing. Inshallah, next time. Okay.